All right, cool. So today, I want to make this, I want to give you guys a lot more chance to code today. So hopefully we'll get through the concept pretty quickly. It will definitely not be as deep and technical as yesterday. It's more of the applications now. And today, what we're going to get into is, of course, what you've all been waiting for. How does ChatGPT work? So I'll go through firstly an overview of that system and talk about the main points at a high level. And then over the next 3 days, today, tomorrow, Thursday's the final session, we'll go through each of the individual training steps in much more detail. And today we'll do step 1, which is supervised fine-tuning. So if you want to open up this this notebook, I'll really just talk through the main points here. But of course, you already are familiar with ChatGPT, I'm sure. You're already familiar with the fact that it can generate very highly competent natural language, stuff that looks really real in a variety of formats, whether it be responding to questions, rewriting input text, writing code, writing poetry, even maybe some form of comedy. All of those things seem to be captured in this system. And this system, as you can tell by the name, is based on GPT. So yesterday, we used GPT, didn't we? We pulled that off the shelf and we used it in Hugging Face. We looked at BERT yesterday, but you can do the same for some of the GPT models. ChatGPT, as described in the most recent blog post, is based on the GPT 3.5 models. So there was, this is basically just talking about the procession of the GPT models. There was GPT, GPT-2, GPT-3, and then GPT 3.5. So ChatGPT is basically goes through a series of processes on top of GPT 3.5, which is like a very big version of the GPT models we looked at yesterday with some other nice tricks. And through these kind of 3 steps, which you can see here, this is how we end up with the system, with the language model that behaves in the way that you probably all played with in the browser. So these are the 3 steps that I'm going to talk through over today, tomorrow, and Thursday. And hopefully, throughout those days, we will, like I said yesterday, be able to build our own little version of ChatGPT. So we'll implement these different algorithms and we'll play around with the results. And I'm going to try and take you guys through as much detail as I can of like how it was done to develop this system based on what we know. We don't know everything because a lot of it is closed source. And of course, we can't access GPT-3 because that's a closed source model. But we'll pull together a bunch of different resources that highlight how some of the parts of this work together. And we'll fine-tune GPT-2 to try and see where we can get to. I don't know how well it's going to work. Hopefully, we'll be able to get somewhere nice. Question? Are you on Discord? Can you help her out with the Discord? And then if you can share the notebook link in there, that'll be really helpful. Cool. Great, yeah. So basically there's 3 steps to this. There's 3 steps to this. The first one is the supervised fine-tuning. The second one is creating a reward model. And the third one is using the reward model to refine the supervised fine-tuning model using reinforcement learning. So we're going to call step 1 SFT, supervised fine-tuning, step 2 the reward model, or maybe RM, and step 3 reinforcement learning with human feedback, RLHF. Those are the 3 processes which I want to cover throughout these sessions, and we're going to zoom in on step 1 today. Give me just a second. Cool, so make sure you got that open in front of you. So the first thing that I want to just highlight is what's the point of each of these steps, right? SFT, RM, RLHF. Well, the point of it is to take a pre-trained language model, like GPT 3.5, and then to get that to perform well in a specific domain and eliminate the kind of bad behaviors which might be present based on the data that was already trained on. So the domain that the GPT models are trained on is like the GPT-2, for example, is, or at least one of them is a very large portion of the internet. You can imagine all kind of things are on the internet, and probably some, nasty, inappropriate behavior, some, and most of it in kind of, varying different tones and consistency. If you want to have a useful chatbot system, you want it to not behave radically and inappropriately in as many instances as possible. And you also want it to be consistent and professional and represent your brand very well if you're going to put it out there, or otherwise face a big backlash, like you might have seen some other companies do. So the point of both step 1 and step 3, supervised fine-tuning and reinforcement learning with human feedback, are to condition this model to behave well in the domain of acting much more like a chatbot system. So step 1 is the simplest of them. Essentially, we take this pre-trained model off the shelf, we gather a data set of examples, and we then and then using basically the same training process which the original model was trained on, we train it on our new data set. The new data set looks like the kind of behavior we want chatbot to perform. It's back and forth dialogue in a chatbot format with responses consistently written and modeled as per instructions by human labelers. So we need humans to write these responses to gather the initial data set. We'll gather several different data sets that we can use across these processes. And the first one is for the supervised fine-tuning, which is prompt and example responses. That's what we're going to train our language model to predict on. We'll look at this in more detail in a second, but we'll basically have this GPT decoder model. We'll take the prompt and the response, which was given in the data set, and try and solve the language modeling task using the decoder there. And at the end of that, we'll have the same model architecture, different parameters. So hopefully the changes in the parameters from the pre-trained model will make the behavior much more like the chatbot style behavior that we want, right? And so we've already seen, supervised fine-tuning used in loads of different domains, from text summarization to question answering, etc., where you take a general purpose model, like any of the GPT models off the shelf, and fine-tune it on that specific domain. What it turns out is that it takes a very long time to get the pre-trained model correct, but it's very quick to do fine-tuning. So roughly, like, the ideal parameters for your fine-tuned model, they're somewhere close to the pre-trained model. So it's a really good starting point. It might be very expensive, very time-consuming to train your large language model like GPT-3, but it can be relatively quick to do the fine-tuning, often done with a single GPU in a few days or less. Any questions about supervised fine-tuning? All right, sweet. So second step is to train a reward model. The reward model, what it does is it takes in a prompt and response pair, and it gives you a single number, a scalar value, which is the reward for that example. How good is this response, basically? Why do we want that? Well, actually, we don't want it for anything particular in step 2, but we use the reward model in step 3. You can see it down there, RK at the end. And what we want to be able to do is to go beyond the data set which we've collected, which contains labeled ideal responses, and be able to evaluate the model's performance even when we don't have new labels, basically. So we use the reward model to evaluate performance. The reward model takes in the prompt and the response generated by the model, and it tells you how good it was. And this you can use in this classic reinforcement learning setup. Reinforcement learning setup is you have some agent, in this case the chatbot, interacting with some environment, in this case the chat interface, and every time it does so, it receives a scalar reward. Big number, you did good. Small number, negative number, you did bad. And what you want to do is use that positive, negative, large, small signal to feedback to how should you update the weights. And all of these steps are going to be done using the same techniques we've looked at so far. Big neural network, input, output, loss, do backpropagation to update the model parameters. And hopefully, through that, we should come up with something that behaves at least a little bit like the system that we used to. Now, again, disclaimer, we're not going to be able to build ChatGPT in 3 days, but we will be able to go through this process, look at the algorithms, look at some small versions of the models, and experience like how the data set was collected, managed, and then pulled into code. Everybody excited? Sweet, good. You look it. Question?
Yeah. For step 2,
yeah.
The first part of step 2, are those samples being generated by GPT 3.5? Or
The examples here, so in step 2, in the first part of the reward model, we're using the same prompts generated from the data set over here. So we basically split this data set into different parts. Some parts contain labels and prompts and responses, which are used in the SFT dataset. Others contain various prompts, single prompt, various responses ranked in order by a human labeler. That's the reward model. And then for the third one, yeah, we've just got these prompts, which come from, again, humans writing them at the start.
Right. So if your second sample is taken from the existing data set, then how are you able to have different samples?
When you say example, do you mean an example?
Like how are you able to have different responses? Because I'm imagining you have to take one sentence from another.
Yeah, so I said in the second part, we're evaluating multiple responses to the same prompt. In this phase of data collection, you have many human labelers. You guys are going to get to play them today, and you may receive some of the same prompts. And of course, you get different responses, and so that fills up the data set with single prompts, many responses. And so, yeah, we should be able to rank them as a result of that. Cool. Any other questions? I see one here.
I want to ask about the reward system. So,
yeah.
The reward is defined by human, or is the neural network which is doing a regression?
It's doing a regression, yeah. So sorry, the question was, I always forget to, or a lot of people always forget to repeat the question. The question was, for the reward model, how to calculate the value? Is it written by a human, or is it done doing a regression or something? So the reward model was trained in step 2, and we'll look at that process tomorrow, but basically, given a ranked set of different responses, you can basically say, the absolute value of the reward doesn't matter very much. What matters is the relative value between those responses. So if someone ranks this as the best response, it should have a higher reward than the one below. And we'll look at a loss function tomorrow, which lets you define how bad that error is. And then once you've got that reward model, you can use it in the third step. Assuming that it's fit model, right? Assuming that the reward model is accurate, it needs to be good at this point. Otherwise, it could be giving you useless rewards in step 3. Does that answer the question? Cool, good stuff. Which one?
So the reward model basically to replace human label.
Yeah. And to kind of, I guess let the model be like in a more free environment to generate its own responses, right? So it can generate all kind of stuff, maybe stuff that you really don't want, that humans didn't intend, or just much more varied data. Yeah. But step 3 and step 1, again, 2 different versions, 2 different layers of doing the same thing, trying to condition the model to behave much more like a chatbot, and with these 2 different objectives. This one's like going to be like, okay, given these good examples, try to emulate that behavior, and then this step 3 is going to say, given that you can tell how good a new response is, like try and make it better. Yeah. So, question?
So what's the difference between SFT and the Pro? Is a 2 modeler?
Sorry, on the right hand side is the PBO. Yeah, so PBO is the optimization, well, is the reinforcement learning algorithm. It comes into play when we look at the loss function. It basically, just to focus on PBO for 1 second, what PBO does is stands for proximal policy optimization. What that means is you have this policy. A policy is something that, in a given situation, tells you how to act. In our case, the situation is what's the prompt. how to act is what's the response I should do. So you want to optimize that policy. That's the second P and the O, and policy, PPO, proximal policy optimization. And the proximal basically just means like, don't make too drastic changes. Stay close to where you are. Stay in proximity and do that gradually. So the PPO is the algorithm we use to optimize this policy over here. The policy itself, what is it? It's that supervised fine-tuning model. Yeah. So this neural network on the left-hand side here, the supervised fine-tuned model, that is this policy. I said it defines how to act in a certain situation. It defines what responses should I give for a given prompt. Yeah.
So in the search that the backpropagation only changed the PPO model, not the SFT.
Yes. No, sorry. So that PPO on the right hand side, that's not the model name. It's kind of labeled actually quite strangely, but on the right hand side, PPO is not the model name. That model is the SFT model. One there. That model is the supervised fine-tuned model. It's going to be optimized using PPO. However, you do make a good you lead to a good point, which is that you've got these two models here. When you do the updates, because you want to maximize this reward model, this one stays fixed. Right, this one stays fixed because you shouldn't be able to game the system, right? You shouldn't be able to change your reward function such that it always gives you a big reward. So in step 2, we'll train the reward model. In step 3, we'll keep the reward model fixed. Great questions, guys. Lily?
I have a question for the reinforcement learning, step 3. It's like that this reinforcement learning with human feedback. It's like you are using this model and you are training it at the same time with the fresh label you got it. Like it is trained and used at the same time.
So not at the same time, yeah. So it's maybe a little bit misleading that this section is like the human feedback section, because the human feedback really comes from the dataset collection. So over here we'll collect demonstration data. That's really used all the way throughout. And so the human feedback is used to train the reward model.
I mean, the human feedback is not that I'm using it. I mean,
no, it's not that.
It's from the data set.
Yeah, it's from the data set. Yeah. No, it's all good. Yeah, I mean you can collect more data to give more feedback. Maybe you just use that in the last step. We'll get to that and we can dive in deep when you want as well.
What do you mean step 1?
Yeah, why do we need step 1 before step 3? I don't know. I mean, they do seem to do like a lot of the same thing, but I think if you were like step 1, it's a proven method that we know works in lots of other domains. That's the first thing I would say. So it's like we know this works for translation, summarization, question answering, and that kind of thing. But just doing that doesn't seem to be able to get you to I think, yeah, to eliminate like a lot of like all of the bad behavior. And so you want to take it further than that. So the reinforcement learning is another layer on top of that. I thought that's not a sufficient answer. I think we can look into that more and maybe dig into it. But I think SFT, that can get you to a good place, and this reinforcement learning can keep you within the realms of good, and update without using labels. So I think the idea there is like the outputs can be much more varied. They don't come from the data set exactly. So I think it lets the model explore in a lot of different ways during the updates. But we should look into that. Alex, if you got something you should share. Cool. All right. Let's move through this then. So is there anything else I want to cover here before we jump into the SFT? Yeah, so, all right, cool, great. So that's really the overview of how the system is trained, those 3 steps. And today, we're going to zoom in on supervised fine-tuning. So if you open this up, the second notebook, as such, then we'll get into here, okay? Now, before we do this, I just want to say that No, actually, we'll do this at the same time. So you guys, I'm going to try and put you, I'm going to do it too. I'm going to put you in the same, as best I can, the same situation that the labelers at OpenAI were in. So we're going to use the same data collection platform and the same kinds of questions to come up with our own data set. And then I'm going to share this with everybody, and we're going to try and optimize against that and write a lot of code today, hopefully. So the first part is actually not going to be using a state-of-the-art labeling platform. But if you click here, I want you guys to each fill this out once. If you're feeling great, fill it out twice. But I've got a form here in that notebook, which you can access, which will let you submit some prompts. The prompts are of two different types. They're either plain prompts, which is just general purpose question answering or instructions. And the second part is few shot prompts, where you give it an example which you kind of want it to continue. And these were two of the categories which OpenAI asked their labelers to use. The third one was for use cases based on feedback to their API. So I want you guys to fill out these plain prompts, and then I'll be able to share. I'll be able to show you the labeling platform which we can get on, create that data set so we can fine tune the model. So have a go at that now.
Where is this on the portal again?
It's in the supervised fine-tuning notebook, which is in the how ChatGPT works pathway. If anybody's missing that, let me know. I've already written some prompts, but it'll be just a small data set if it's only me. So if we can all do it, it'd be really great. Boom. Oh yeah, so in that case you should just do like a bullet point. All right, so let me give some examples. I'll go through plain prompts and then we can look at the few shot prompts because maybe I wasn't clear enough about what that means. So plain prompt one, let's do like explain to me how I can lose weight. It's tiny, isn't it? All right, next prompt. What's the best type of car I can buy for my family? My family with 2 kids and a dog. Plain prompt 3. What's that? That's embarrassing. All right. Cool. Plain prompt number 3. It's harder than you think, isn't it? Coming up with the prompts. Okay, cool. What should I go with here? Like, write me a story about a wizard. Cool. And the few shot prompts. This is the one that might not be so obvious. So you'll see some examples I've given in Scale in a second when we look at those. But few shot prompt number 1, maybe I would do something like, if I knew another language, I would do something like this, English word to like use arrows here or something like that, like French word. or you could do something that's just like a set of items which are all in the same category. So, so I could do like breeds of dog, do Dalmatian, pointer. Have I done something embarrassing again? No, no, we're good. All right, let's not worry about that for right now. There we go. Okay, cool. There's some different dogs. There's a few shot prompt. Here's a few examples. Please continue this. So it should be able to, you guys should be able to figure out, you know, how to label those things, and the system should be able to understand that these are groups of things that are linked together. And what that should hopefully allow the model to learn is that those things should have similar representations. Well, depending on what the prompt is, I might have something else. So dig back into that. These are optional as well, so if you really can't think of any, please just submit, and then you can get your prompts in there. If you're on a creative high, then just do it a few times. Give us some more prompts. The more data we got, the better. The better this is going to turn out. I don't know what the outcome is going to be, but at least we'll see how it works. Take a few more minutes to do that, and then we'll jump back in.
Someone else is saying question, and I think it's a really bad diagram. Should go across to our surface. All those white nodes, fragments in here. So I'm thinking in the kind of in the 3D dimension, you see backwards. That's each
So what happens when you do one of these like is this not like
no, so it's white there. For example, is so only we feel will be how this query metrics applied on each word independently.
right? So you end up in this case with a 5D query for each.
So what constraints?
The two axes there are literally the element of the input and the element of the output. The weight between the two. How much is that input? So basically, value in this price comes from the sum. Question is, well, for this, they're all these are all plates, which you can multiply by the values and these like nodes. And then add a diagram. A little bit more nicer. It's like using a system. All I'm saying is take for a single factor representation, create a new combination of it, which is a new method. Just single linear layer. That is the layer has the parameters.
Yeah, I know it.
You've got like you've got a sequence. These are called d-dimensional vectors, and they go into some. They go into classical one. So coming like that. But this is happening not just one head. This is happening. Each of them go in, and what happens to each of them is I do a matrix multiplication with that method to get a query, T, and a K. Right, and then it's going to so this is the vector, and this is why my diagram is very bad, because I feel like you pay the T here, and I also use that in a diagram for the parameter between this layer, right? So what you really want is you want to say like, okay, Q, or in lowercase q, for the vector query, that's equal to some weight matrix, which goes from, let's say, let's call it WEQ, goes from the embeddings to the query. That applies to the embedding. That's for all embeddings, right? So you get QI to that.
Right.
Yeah, the same way matrix applies to each. So all of the words are projected to get their keys through the values in the same way.
But if your weight matrix is saying how much you care about first word, second word.
No, saying how much you can care about first element in this embedding. How much that can contribute to the first whichever element. Yeah. If you've got a weight matrix which is equal to something like that in space. Which is, let's say it's going to be full of real numbers. What shape is it going to have? It's going to have dk by d. Right. Because it produces a, it's multiplied by, yeah. So the n dimensional match, this is d-dimensional, so this is d-dimensional, the output is k-dimensional, and that's the dimension of the output.
But this only allows you to say, I want you to focus on input one case. What's unique case? So what is your main concept?
Because so this is so just to be really clear, right? This is just a single word. No, sorry, this is just a single word.
Yeah. Yeah.
And you do that for log I equals 2, this is what I equals 1, and you do 8. That's what I equals 3.
So each of those different embeddings will get multiplied by the same weight mixture calculated to the got it now? So that's happening parallel across the nation.
Yeah. I'm just struggling to find how is it able to do for arbitrary long
How are they able to do that? So you end up with 2 kV for each of these two works, right? 2 kV. This one. These ones are for this one. And for this one, we get again 2 kV, right? They're all independent. So far. All independent, right? And then we can keep the attention. The attention is a matrix like that of size, we call it T by T. That's the sequence length. And so in that matrix, you have basically different values which represent the attention that input I pays to input J. Take the softmax over that, and they give you a distribution. Yeah, these values then are Q10. Exactly. So to be more concrete, values that shape. The one in the middle here will be like QI by K. This one down here would be QT by K2. This one over here, Q, yes, we're saying that to QT and K1. That's the cosine for the line. That's how we compute the attention scores. Okay, so that we get weighted. And so the interesting thing is what happens next, right? It's like you have these values, and they basically say they get multiplied by V because the overall equation is softmax QK multiplied by V. So basically, the interesting thing is what V, the weights which are used to sum up the V's, you think about them like weights in a neural network layer. Usually the weights between each layer are fixed. They're fixed for every event. When you train your network, you don't change the parameters, the weights are fixed. They sum up the output. In this case, they change for every event. So the weights of how different values are together change based on how similar the vectors are. So you get these layers transformations where how they stretch and squeeze the space is dependent on what the input values were, which is very subtle. Does that make sense? We got to say that. So yeah, in the diagrams, in the attention equation, which I'm talking about, this is like a vector. Oh, sorry, I made this first thing. So Q is equal to Q1 all the way to Qt. And then this basically just makes a notation for doing the dot product there between each combination. Nice.
Okay, cool. So, recap of attention. We did that. Hopefully we got some nice prompts now, and we're ready to take it to the next stage. So, hopefully, bunch of prompts, lovely, good stuff. Okay, so I've got all those in a Google Sheet, and I am gonna, sorry, there they are in a Google Sheet. Here they are formatted. Now, I want to introduce you to the platform which OpenAI actually used to collect and annotate their data. Unfortunately, I only get two free projects on it. So I use the first one in Google Forms, and we'll do the other ones in Scale when we do the data collection. So what I want to show here this is what the platform Scale looks like for data labeling and management. Let's just take a look at Scale firstly. So Scale is like a platform for collecting better data to do better AI. They do all kind of things, from annotation to data management, data labeling automation, evaluation, collection, and even generation at the end. We're just going to focus on the annotation and the managing. But one of their products is called Scale Studio. And what this allows you to set up is projects, which I've set up here. I've called one Supervised Fine-Tuning. And their definition. You can set up, okay, what's the basic type of problem I'm working on? What's the data format? What's the taxonomy of the data? Which is like, okay, basically, you know, how should it be labeled? You can add different types of labels. In my case, what I've done is I've got all your prompts. I'm going to get them in a second. And I'm going to put them in here as tasks with a text response. Then I can set instructions for how to view this and so on. So if you have projects you want to work on as well, you want to manage the data appropriately, not doing it in Google Form like we just did, then you could use Scale. In here, I've got my data. I've only got a few data points so far. Here they are. And I'm going to upload some new data now. So I'm going to go back to the sheet. I'm going to file, download this as CSV. I'm going to go back here, upload data, and I'm going to drag that in. What we should get from this in a moment, once it processes, is updated data in here. So we've got a bunch of examples. Nice. Some foreign languages. Tough stuff. All right, so here we got a bunch of different examples, and they're going to be formatted in the same kind of way that I've already got this problem laid out in my problem definition. Now, what I can do is I can create a new batch of data. I'm going to go to this batches tab, add new batch. I'm going to call it my third batch. Continue. I will select the items via filter. There's 248 items in here. Nice. Let's put all of those into a single batch in order. And I'm going to create that batch. Now, I got a lot of examples in a single batch. I want you guys to see what it's like from the other side, which is as a labeler, how should you access this? Well, to do that, if you go back into the notebook, there's another Google form here. If you hit that link, fill out your email, it's just a single question on your email, in that Google form, and I'll add all of you to Scale so that you can help us label this data. So after that, we'll write some prompts. Then we'll have a CSV file which contains prompt response pairs. We'll pull them into Python. We'll create a data set from that. So take 1 minute just to go into here, submit your email. I'll add you into Scale. And then we'll take the next step. Sorry. Cool, so I'm going to go to my labeler management on scale, click labeling team, then I will invite members, and I'm going to paste your emails in there. Cool, so I've added you all to scale. Anybody got the email yet? That come through? Cool, good stuff. If you don't have it, let me know. But you should all get an invite to scale and be able to see something that looks more like this. So this is scale from another perspective. This is the labeler perspective. So this is the same kind of thing that the labelers would have experienced creating the OpenAI dataset. We've got a dashboard and it contains my queue, supervised fine tuning. I open that task queue and then I can fill out the responses. So let's have a look. Take a look at that and I'll walk around. Let me know if you've got any questions. We'll take maybe a little longer to do that. Let's take 15 minutes to do that. Again, I'll answer more questions if anybody's got tech stuff they want to review as we do that. Yeah. Did you submit your email to the Google form?
Yes.
Cool. You haven't received it either. Raise your hands who's received it. Okay. Let me check. Okay, yeah, there's a bunch more of you now. Try now. You got it. Still not receiving the email. Okay, yeah, so oh god. All right, yeah, so have a look at that. All right, yeah, so take a go at labeling those. I'm gonna come around the room now and help out with anybody who's not got access. All right. Wow. What's your email?
Peyton.hammersley. Peyton, yeah, that's it. Yeah. Strange. That is, yeah. Sorry.
Okay, yeah, so I'm just gonna create that data set from all the downloaded responses. Okay, there we go. Got it. Okay, so now I've got this big raw file. It just contains dictionaries of prompt response pairs. Here it is. And what I'm going to do is I'm going to take that and put it into my... I'm going to put it into Discord and share that with you guys so we can build a data set from it. So give me a sec, watch us just do that. So I'm going to drop this in the Oxford announcements channel. It's going to be a JSON file. And then I'm going to need you to upload this to Google Colab. So let me know if you can't access that. The dataset is in Discord. Then we got a few things to do. All right, anybody having trouble with the dataset there? Nice, we got the dataset. So, what you should do now is come to Colab, hit this button, and wait for it to start up a runtime. We want to upload this file. Hit this button to upload the file. And, or maybe I can just drag in that one, which I was just using. There you go. All right, cool. So now I've got the file raw data one. It's called raw data one.json. It's called, and it's in my Colab notebook. So I've got to build a data set quickly. Can you guys help me with this? Who remembers how to build the data set? So what does the initializer do? Somebody help me out. What does this method do here? Alex?
Just lets you find
anything that you need later on, you want to set it in here. So what do you think I'm going to load in the initializer of this data set? Create an instance of the data set. Of course, I need the file. Yeah, so how would I read in that file? With open. Yep, so in the context of this file being open, give the name of the file, raw_data1.json. Call that F, and then what do I do with that? Use json.load. Yes, thank you. Was that Ishwa? Json.load in the file, and I can say that's equal to data. So I'll say self.data is equal to that. Let's just run this and check it all works. So I'll print a data set. .data. Run that, see if we got it. I'm happy with running this cell. It's all good. Cool. So that's what it looks like. So I've got this list of dictionaries. So you can see each dictionary has a prompt and a response. That's great. That's exactly what I need to train my supervised model. I'm going to stack those things together and do language modeling on them. Length. How do I return the len? Any suggestions? Len self.data. Exactly. What is that? What does the len method need to do? Why does it? Sorry, I gave it away there. It defines the length of the data set. Yeah, easy one. Cool. It gave away my comments. Get item. So this one defines how to get a sample from the data set by indexing it. It should return a pair of the prompt and the response. Anybody want to help me with this one? How would I go about doing that? I've got my self.data. I've got an index passed into here because when you index with square brackets, you've got to put a number in those brackets. Nice, I like that, yeah. So I want the example at that index. Brilliant. Yep, and then I want to get the prompt from that. So that's the first thing I want to return. What next?
And then the same thing, but with
yeah. That looks pretty good to me. Nice. Something like that. So let's run this. I'll delete printing the data. Let's just get what a single example looks like. Nice. It's a tuple. You can tell by the round brackets. That's just a it's just a immutable set of items. So the first thing is the prompt. The second thing is the response. So now I want to iterate through this data set. I'm going to get different prompt response pairs. Is this large enough? You guys want me to zoom in? Raise a hand, zoom in. Cool. All right, there we go. So you should be able to iterate through my data set now. There's the full solution. You guys have got that in your own notebooks. So just another comment to mention what we talked about earlier. GPT 3.5, not available publicly. GPT-3, not available either, only through the API. So you can't get your hands on that with that. We probably wouldn't be able to run it on this hardware anyway, because it's massive. The GPT models, GPT-3 models has 175 billion parameters. We're going to use GPT-2. Has a lot of parameters, hell of a lot of parameters, but small enough that we can run it on a single machine. They're trained on different data sets and they achieve different performance. Of course, the larger models are more performant, but much more energy and time consuming to run. They're just the same model, but larger, essentially. There's probably a few little changes. But in the next cell, we've done this before, so you should be used to this. This is us loading in the GPT-2 model and using it to complete a prompt. So if I run through this, what's happening here, I'm just getting that GPT-2 config class, using its from pre-train method to get the GPT-2 model, and I set this flag, output states hidden to false. I don't need the output states, output hidden states, I don't need the hidden states. I just need the predictions from the language model head. That's fine. So I'll get language model head predictions at each time step. That's a distribution over the next word. I got the tokenizer in the same way, and then get the GPT-2 model in a similar way using GPT-2 LM head model class. Give it a prompt, encode that prompt using the tokenizer. It gives you a list of IDs, and then you can call model.generate to generate new text from that. So this is kind of like what you would use once the model is trained, this method. This we don't need to do this during training because we can just pass it all through and calculate the loss. We don't need to generate sequentially, which is what this one does. Emits one word, feeds it back to the beginning, and so on. Finally, decoding that, you get the response. So let's see how good GPT-2 is so far. With the prompt, hello, I'm a language model. I need to probably install transformers by running this cell. So install the Hugging Face transformers library. Once that's done, I should be able to run this. That, loading in the binary files containing the weights of GPT-2, 1.5 billion parameters straight into your notebook. The language model is yours to use there. It gives you a little bit of a warning here, and then it gives you your prompt and completion. Hello, I'm a language model, a model of languages. I use languages, concepts of ideas, and so on. It's quite obvious now, but one thing I noticed after that experience is that one language is better than several languages. So that's the kind of thing that GPT-2 is going to generate so far. How does it do in like a chat conversation? Let's have a look. I've got a function down here, utility function called chat. And if you run this, it's going to engage in a back and forth chat with you. It just continually loops, asking you to give an input, adds that to the prompt so far. Then encodes that prompt and generates from it. Once you get your output, it decodes that and says that's what came from the bot. I thought I'd had bot written there. Something like that. Nice. So run that, and it should. We basically begin this conversation, right? So you, hello there. Can you help me with ideas for my brother's birthday? Party. Kind of thing people have been asking ChatGPT for some reason. So run that, and it says it's predicting right now, I hope, or it's predicted empty, in which case something's going wrong. So you see what it's done. It's done something not quite right, and we're going to need to both train it that this is not the kind of right response, and maybe add some other kind of manual fixes in there. So, you know, I don't know what's going on here. So there you go, right, and so on. So have a go with that. Run the function, make sure you understand the function, and then we're gonna, of course, this is the untrained model. We're gonna run it again after we have fine-tuned this model. So the meat of this is coming when we do the fine-tuning. Run that function. Largest laugh. I'll come and check out what the response was, and then we'll move on to actually implementing the training loop, which fine-tunes this model. All right. It's inappropriate.
In general, but there is a max like well, I mean, I'm not sure we're gonna get it. Yeah, I think it's this. Like this is one of the so basically, like I said, how many people exist in the world? And said one doesn't work. It's random.
Okay, cool. So the generations aren't great, right? GPT-2, firstly, it's a small model, not as capable as GPT-3. GPT-3 was already a pretty big deal when it came out, much more significantly than GPT-2. But the generations aren't great in general. You know, I've seen a lot of like just lots of exclamation marks, lots of underscores, that kind of thing. It's repeating itself, all sorts of bad stuff. This one is actually a pretty good example as far as these non-tuned models go. So the next thing that we want to be able to do is to tune the models. I'll run through that, and then we can play around with some of the parameters of everything in here. People were asking things like, well, okay, what does the top K do? What does the top P do? Etc. You can see that stuff in the inline documentation here. My friend who was asking about the generate function, he's absorbed in his model right now. But you can see everything that's going on inside there. So we've got the different parameters. Whatever you want to look at, you should be able to find it in there. Otherwise, I believe you should be able to follow these docs somewhere or look them up. But we'll come back to that at the end. So how do we fine-tune this model? This is the question. I'm going to do the key parts of it in the cell, and I want you guys help as we go through it as well. So overall, right, we're going to have the usual train function that we had previously. In this case, the data set is the supervised fine-tuning data set. Then we've got the data loader. We create the optimizer as usual. I looked in the papers for the Instruct GPT models, which is a sister model to ChatGPT developed about a year before. And these are the parameters that they're using for the training. I set up my logging, creating a TensorBoard summary writer so I can launch TensorBoard shortly. And then I'll be able to see my loss change in which I'm going to log. I'm going to go through the data set a number of times. I'm going to go through each batch in the data set in one epoch. And in that batch, I've got the prompt and the response. That's a duplicate there. It shouldn't be there. So the prompt and the response, they're the two things in the batch. And then here's where the interesting stuff needs to happen, basically. So firstly, like the overall thing is, how am I going to train this? I'm going to get the entire text, which is the prompt plus the response, into one string. And then I'm basically going to say, here's an example of a language that you should be able to model. So I'm going to pass that all through the transformer, and the output of the transformer in this language modeling head case, remember my model is an instance of the GPT-2 language head model. The outputs are going to be those distributions over the words for each different sequence, for each different token in that overall sequence. And what I want is that for each given position, it's correctly predicted the next word. So firstly, get the entire text, and then I'll tokenize all of that text using the tokenizer. I add this start of sequence and end of sequence keys, which are start of sequence and end of sequence tokens. These are the start of sequence and end of sequence tokens used to train ChatGPT that the tokenizer is familiar with. So it will have a representation of those, and the model should be able to predict, okay, this is the end of the sequence, this is the start of a sequence, understand what that means, and such. Note here that previously we've been using tokenizer.encode, and here I'm just calling tokenizer. With this tokenizer, when I call tokenizer on any input text, it returns me this thing which I've called the context dictionary, and that contains each of these three things as attributes. Not just the input IDs, but also the labels, so I don't have to manually shift them along myself, because they'll just be the same tokens shifted in one position left, but also the attention mask as well. And remember, I need to give my model the attention mask so that it pays 0 attention to anything that came previously up to that point. So that's very important here. So for my input IDs, I will get that context dictionary. And I'll get my inputs, input IDs, is it? Labels is going to be something similar. And attention mask also similar. So I've got those three things. I'm just going to print my context dictionary as well, so you guys can see what that looks like before we run this in loop. And handy trick, I'll just kill my code there with the undefined variable. So I run that, it says can only concatenate string, not a tuple, to a string. So what's happening there? So the prompt and the response is equal to the batch. Apparently one of these things is a tuple. So let's print those and take a look. Desk bottle, what's going on here? So what is that example? Something's gone wrong with my data loader up above. When I do the get item, let's just print what I'm returning so we can get an idea of what that is. So I'll just run that cell to redefine that. Come back down here, run this again. What's the issue? Okay, right, so this time you can see the issue more clearly because it's just a plain input rather than bullet points looked like previously. So I've got, each of them comes out as a tuple. So I just need to get the 0th item in each of those tuples. So that actually wasn't a duplicate, what I said above. So the prompt is the prompt 0 and the response is equal to the response 0. Why would that be? Have I messed something up above? Have I returned them in the wrong format from my data loader as a tuple? I'm not sure. If someone wants to figure that out for me, that would be great. But I should just be able to index that tuple. Looks like they've only got one item in. That'll get me the prompt and the response. Now I should be able to stack them together, get this context dictionary, and print it out. So let's have a look. All right. What's happening here? All right, I've got an attribute error. Somehow it doesn't show me the whole error, annoyingly. That happens on line. Where's the whole trace back? Okay, context dict.labels was not found, so I'd probably need to look at something different. So here's the context dictionary. Here's what's get returned from the tokenizer: input IDs, attention mask, and that's it actually. Yeah, so I don't actually have separate labels. What I remember here is that you can actually just use the input IDs as the labels, and the shifting them one position along, that happens inside the model GPT-2. So how do I know that? Well, you can look it up. GPT-2, Hugging Face. Let's have a look at the docs. Here's the documentation, or at least here's the model card, which tells you all about this model, what it's used for, and everything like that. But I actually want not the model card there, but the documentation for the model. So if I click on that second link, just get familiar with Hugging Face, but that's the link to the model card. This is the link to the documentation for that model. And in here, you'll see, if you scroll down, you can get these different parts of the model. Language model head. Here's the forward method. This makes the predictions. So if I expand that, then you can see it takes in the input IDs, it takes in the attention mask, it takes in the labels, and it says here, note that the labels are shifted inside the model. That is, you can set labels equal to input IDs. So that's what I've done in my code. Not that code. This one. So my labels are basically the words that should be predicted, and the input IDs are the same. They get shifted along inside the model. Now I can do the forward pass, basically. So I can say model, I just call my model. That'll get me my outputs like that. I can pass in the label, the labels equal to, well, I can pass in the input IDs. The labels and the attention mask. And I should be able to get this output prediction. So looking back to the docs, what does this return? It returns this thing, which apparently has these different attributes: loss, logits, hidden states, attentions, cross attentions, etc. So if you're interested in seeing what's happening when you make these predictions, you can look at all those values inside. In my case, I just want the loss. So again, the model computes this inside. This is the measure of how bad the model is doing for the language modeling task, because this is the language modeling head. And once I get that loss, I can do the usual. Loss.backward, set the gradient attributes of all the model parameters, optimizer.step, update them, optimizer.zeroGrad, reset them. And I should, if all things work, be able to run that fine. Nope, not at all. Something's gone wrong here. The list object has no attribute size. That's probably because it's not a torch tensor. Where has this happened? This has happened. All of this, yeah. So those things should be torch tensors, likely. Good debugging there from you, Peyton. All right, run that. What's going to happen now? Let's see. It's training, okay? I'm going to stop that because I don't want it to print out all of this stuff every time it does this. So I run this again. And we should begin to see batches get processed, okay? So the data is going through and the model is updating. Cool, and as that's going, we should be able to look at TensorBoard as well. I don't have the extension installed right now. So you guys go ahead and run that, and then I'll get this set up and we can visualize it to wrap up. Eunice? The attention mask is a triangular lower matrix, which has ones where the model is allowed to pay attention to, where the head is allowed to pay attention to for each different token, basically. So the token on the left should only be able to pay attention to the first input. The next token should be able to pay attention to the first two, and so on. Print it out. If it doesn't make sense, let me know. Cool. All right, so final thing, I will just show you guys what this training looks like. I'm going to kill that. Run these. Launch TensorBoard, and we should be able to see the training so far. And you should see this curve going down gradually. All right. I'll train this for longer later, and I'd like you guys to all train it as well. There's some bonus challenges here for you to look into. But you can see here, loss goes down. Loss goes down over time, and that's good, right? That means it's getting better at predicting the next word in these kinds of sequences that we've given it from the new data set which we created. The question is it getting better qualitatively? So that's what I'd like you guys to explore. One of the challenges there is to log the text to TensorBoard. So once you do that, you'll be able to look at the text, and you can see over time, right, do these responses look more and more appropriate to the given prompt? With that, guys, I'll wrap up there. Any questions, feel free to hang around after. All of the solutions are available in that notebook. It should work as is, running it. And other than that, let's get on to step 2 tomorrow, where we'll be building the reward model. Thank you very much. For sure. Which part? Oh, this one, yeah. Lily? You want me to come over there? 1 sec.